Your roof cost $15,000. In 25 years, it will be garbage. A medieval peasant with zero money and zero technology built a roof that lasted 50 years, sometimes longer. This was not luck. This was not primitive guesswork. This was engineering. And when you understand how they did it, you realize we have been building roofs wrong for a century. Today we are going to rebuild that roof, layer by layer, step by step, because the secret is not what you think. Section 1. The problem. Modern asphalt shingles fail in 20 to 30 years. You accept this as normal. But there is something wrong with that acceptance. Medieval Europe faced winters that killed crops, froze rivers solid, and buried villages under snow for months. The Great Famine of 1315 to 1317 showed what cold could do. Your home was not a comfort, it was a fortress. And the single most critical defense was the roof. A leak was not an inconvenience, it was a catastrophe. Water spoiled grain stores, rotted timber frames, created damp cold that turned coughs into death. In an age without modern medicine, a dry house was survival. The pressure to create a durable, waterproof, well-insulated roof was immense. It was literally life or death. Out of this necessity, an incredible system was perfected. And we forgot it. Section 2. The frame engineering flexibility. Every great roof needs a skeleton. The medieval solution was the cruck frame. A carpenter selected a large oak tree, ideally one with a natural curve. After felling, they split the trunk lengthwise. This created a pair of perfectly matched curved timbers called blades. These were raised and joined at the peak, forming a massive A-frame. But here is what makes this genius. The cruck blades extended from the ridge of the roof all the way to the ground. This design transferred the entire weight of the roof directly to the earth. The walls became weather screens, nothing more. This saved materials and labor. But the true genius appeared during extreme weather. The A-frame geometry is inherently stable. The curve of the oak blades allowed them to flex under extreme loads, heavy snowfall, high winds, and then return to shape. Modern structural engineers recognize this principle in earthquake-resistant buildings. The medieval peasant mastered it 700 years earlier through observation. Several cruck frames connected by horizontal beams called purlins formed a powerful skeleton, ready for the layers of protection. And those layers were not random. They were a calculated defense system. Section 3. The hidden shield. Turf, bark, and regional variation. Before any thatch was laid, the most resourceful builders added a secret weapon, a complete underlayer. And this is where regional genius appears. In southern England, turf was king. Cut in large sections from pasture, a living mat of soil held together by dense grass roots. In Scotland and northern England, where turf was scarce, birch bark dominated, harvested in large sheets, naturally waterproof, thanks to oils in the bark. In the Highlands, heather served double duty, both as underlayer and sometimes as the main thatching material itself. In Wales, particularly South Wales, builders used a combination, turf base with straw on top. The turf was laid in alternating layers with stone, a technique that lasted into modern times. Let's focus on turf, because it reveals sophisticated thinking. When laid on the roof, turf sections were heavy, 10 to 15 kilograms per square metre, 30 to 45 pounds per 10 square feet. This secured the structure against wind. But that was just the beginning. The dense peaty soil was remarkably water-resistant. The root system created a tough fibrous layer, difficult for water to penetrate. This turf layer performed multiple critical functions. First, the ultimate fail-safe. If driving rain found a path through the thatch above, it met this second barrier and was shed away. Second, incredible insulation. Thick earth has high thermal mass. It absorbs and releases heat slowly. In winter, this trapped heat from the fire inside. In summer, it kept the interior cool. Temperature swings inside the house were dampened by 20 to 30 degrees Fahrenheit, 10 to 15 degrees Celsius. Third, moisture regulation. The turf absorbed ambient moisture from inside the house, from cooking, from breathing, from animals, and released it slowly through the outer layers. This prevented condensation from forming on the underside of the thatch. Condensation is the silent killer of modern sealed roofs. Water vapour from inside the home hits the cold underside of modern roofing and condenses. This moisture rots structures from the inside out. The medieval system, by incorporating breathing layers, had elegantly solved a problem that still costs homeowners billions annually. Birch bark worked differently but equally well. Harvested in early spring when sap was rising, the bark could be peeled in sheets up to 6 feet long, nearly 2 meters. The natural oils in birch bark made it waterproof. Overlapped like shingles, it created an impermeable membrane that lasted decades. Some northern builders used both, birch bark as the waterproof membrane, turf on top for insulation and weight. In archaeological excavations of medieval buildings, these underlayers are often the best preserved elements. The main thatch weathers and is replaced, but the turf and bark, protected beneath fresh layers, remain intact for centuries. One excavation in Yorkshire revealed a turf underlayer with grass species that had been extinct in that region for 400 years, preserved perfectly under 16 successive coats of thatch. This was not a single-layer roof. This was defence in depth, and we have not even reached the main event yet. Section 4. The Smoke Secret. Here is something modern people miss entirely. Medieval houses had no chimneys, not at first. The hearth fire sat in the centre of the room. Smoke rose and filtered through the thatch before exiting. This seems like terrible design, until you understand what the smoke was doing. First, it was killing bugs. Insects that would normally infest thatch died in the smoke. Beetles, moths, larvae, all dead. Second, it was waterproofing the thatch. Smoke contains hundreds of compounds. Many are antibacterial and antifungal. They penetrate deep into the straw and create a preservation layer. Analysis of smoke-blackened medieval thatch reveals something remarkable. The straw is essentially mummified. Bacteria cannot grow. Fungi cannot establish. The thatch becomes nearly inert. Third, the smoke was preserving food. Meat hung in the rafters was naturally smoked. This was not accidental. This was intentional food preservation built into the architecture. Archaeological excavations have found medieval thatch so heavily smoke-blackened it appears charred, but analysis shows it is not damaged. It is preserved. In fact, smoke-blackened thatch is now called the jewel in the crown of medieval archaeology, because the smoke preserved not just the straw, but also the seeds and crop weeds mixed in with it. Archaeobotanists can examine this ancient thatch and identify crop varieties from 600 years ago, many now extinct. They can determine what people were farming, what weeds were common, even what bread people were eating. One analysis identified wheat varieties that grew to 6 feet tall, nearly 2 meters. These varieties are now illegal to grow under UK law. The smoke also created a natural fire retardant. Modern analysis shows smoke-treated thatch is significantly more resistant to ignition than untreated thatch. The creosote compounds in smoke raise the ignition temperature. Chimneys arrived in the 12th century, but only for the super-rich, monasteries, castles. For everyone else, the central hearth and smoke-filled roof remained standard through the 1500s. This was not primitive ignorance. This was integrated systems thinking. The smoke that seemed like a problem was solving multiple problems simultaneously. And when chimneys became common, thatched roofs actually became more vulnerable. Without smoke treatment, insect damage and rot increased. Thatchers had to develop new preservation methods. Which brings us to the craft itself. Section 5. Thatching Technique. With the frame secure and underlayers in place, it was time for the thatch itself. This was not simply piling straw on a roof. This was a highly technical craft with regional variations that reveal sophisticated understanding of materials. Material selection came first. In southern England, wheat straw dominated, specifically long straw. Old varieties grew to 6 feet tall, long strong stems. In East Anglia, water reed was king, harvested from marshes. The Norfolk Broads produced the finest quality. In Devon and Cornwall, combed wheat reed was preferred, processed differently than long straw, cleaner, neater appearance. In Scotland and the Highlands, heather and broom were common, where cereals were scarce. But water reed was the undisputed champion for longevity. Here is why. Water reed grows in marshes. As it grows, it absorbs silica from the water. This creates a hard, waxy, naturally waterproof coating on the stem. This silica coating makes water reed exceptionally resistant to rot and insect damage. Water reed could last 50 to 60 years on a steep roof in favourable conditions. Even in wet English weather, properly installed water reed lasted 40 years minimum. Compare this to long straw at 20 to 30 years, or heather at 25 years. But water reed required specific technique. The material was harvested in winter, frozen marshes, cut by hand initially, later by specialised machines that walked on the ice. Harvesting timing mattered. Cut too early and the reed was not fully matured. Cut too late and spring growth interfered. The reed was bundled into tight sheaves. Each bundle approximately 8 inches in diameter, 20 centimetres, tied with willow or later with tarred string. The thatcher began at the bottom edge of the roof, the eaves, and worked upward. Each bundle was laid and secured. The next layer overlapped the one below by 2/3, like modern shingles. This shed water downward with no penetration points. The bundles were held in place using spars, sharpened twisted stakes of hazel wood. Each spar was 24 inches long, 60 centimetres. The spars were driven through horizontal rods called liggers, flexible hazel or willow rods laid across the thatch. The spars pinned the liggers down and stitched through the thatch into the underlayer. This created an interconnected matrix. Wind forces were distributed across the entire roof, no single point of failure. For a typical cottage roof of 100 square metres, approximately 1,000 square feet, a skilled thatcher used 8,000 to 10,000 spars. Every spar handmade, split from hazel, twisted while green, sharpened at both ends. The thatcher worked from a ladder propped against the roof. No scaffolding for most jobs. Speed and efficiency mattered because weather could change. A skilled thatcher could lay 1 square metre per hour, 10 square feet per hour. A full roof took 2 to 3 weeks. The final step was dressing the roof. Using a wooden paddle called a leggeta, the thatcher beat the ends of the straw upward. This was not cosmetic, this was structural. The beating compacted the material and created a dense, smooth surface. Water falling on a properly dressed roof had no choice but to run off immediately. The finished main coat was 12 to 16 inches thick minimum, 30 to 40 centimetres, a solid monolithic shell. But here is what most people miss. This was not the final roof, this was the first coat. Section 6. SPAR coating and accumulation. Modern roofing is replacement roofing. When it fails, you tear it off and start over. Medieval roofing was accumulation roofing. When the outer surface weathered after 20 or 30 years, medieval thatchers did not strip the roof. They added a new layer on top. This technique was called SPAR coating, and it changes everything. The old thatch remained. It had compacted, settled. It was still waterproof underneath. It added mass. It added insulation. Removing it was wasted labour and wasted material. So they laid fresh thatch directly over it, secured it with new spars, dressed it smooth. The new layer bonded with the old through compression and the interlocking of fibres. This process could repeat multiple times over centuries. Archaeological excavations of very old buildings have found that accumulations over 7 feet thick, over 2 metres. Layers upon layers, each generation adding to the work of the previous. One building surveyed in Somerset had 15 distinct layers. Carbon dating revealed they spanned from 1320 to 1760, 440 years of continuous maintenance without full replacement. Each layer preserved below like archaeological strata. This is how some medieval roofs lasted not 50 years but 200 years or more. One thatcher's journal from 12 documents SPAR coating a roof that his grandfather had originally thatched in 1638, 74 years of service. Still functional. This was maintenance designed for the long term, not for planned obsolescence. And it created an unexpected benefit. The accumulated layers added significant insulation. 7 feet of thatch provides insulation value equivalent to modern insulation rated at R60 to R70. For context, Modern building codes require R30 to R40 in cold climates. Medieval buildings with thick accumulated thatch were thermally superior to most modern construction. But this system had requirements. The roof structure had to support the weight. 7 feet of thatch weighs 150 to 200 kilograms per square metre, 30 to 40 pounds per square foot. This is why cruck frames were essential. They carried weight directly to the ground, no stress on walls. And the pitch had to be steep, 45 degrees minimum. Steeper meant faster water shedding and longer life. Which brings us to the question everyone asks: if this system was so effective, why did it disappear? Section 7. The death of a system. The decline was not because better technology arrived. It was because of deliberate economic and political decisions. The first blow was urbanisation and fire codes. In 1212, London banned new thatched roofs after a major fire. Existing roofs had to be plastered with clay or removed. Other cities followed. Thatch became illegal in dense urban areas. Reasonable concern. Fire spreading roof to roof was genuinely dangerous in medieval cities built of timber. But this created a cultural shift that became associated with rural poverty. Tiles and slate became symbols of urban sophistication and wealth. The second blow was the Industrial Revolution. Canals built in the 1700s allowed Welsh slate to be transported cheaply. Railways in the 1800s made distribution nationwide. Slate was expensive but permanent. Once installed, minimal maintenance for 100 years. Thatch required constant attention. Patching, SPAR coating every 20 years. Full recoat every 40 to 50 years. In a cash economy with wage labour, slate became economically competitive despite higher initial cost. But the killing blow came from agriculture. Medieval wheat grew 6 feet tall, nearly 2 metres. Long stems were essential for quality thatch. In the 1880s, new short-stemmed wheat varieties were bred. These produced more grain per acre, 40% more yield. For farmers, this was revolutionary. For thatchers, this was catastrophic. Short stems cannot be thatched. They are too weak. They do not overlap properly. They do not last. Then came the combine harvester in the 1930s and 40s. This machine threshed wheat in the field, fast, efficient. But it mangled the straw, rendered it useless for thatching. Traditional hand threshing preserved straw integrity. Combine harvesting destroyed it. By 1950, quality thatching straw was nearly unavailable in England. But here is the part nobody talks about. In 1964, the UK passed the Plant Variety and Seeds Act. This law made it illegal for anyone to give, trade or sell seed of older wheat varieties to a third party for growing purposes. Subject to significant fines. Read that again. The government made it illegal to grow the wheat that created functional roofing material. Why? Because modern agriculture prioritizes grain yield. Short stems mean more grain per acre. The fact that this destroyed a roofing industry that had worked for 1,000 years was deemed irrelevant. The law is still in effect. Today, over 80% of water aid used in the UK is imported from Turkey, Eastern Europe, China, South Africa. The local ecosystems that produced thatching materials for millennia have been dismantled. Thatchers in the UK can no longer obtain top-quality thatching straw grown from traditional tall-stemmed wheat varieties. A small number of specialty growers cultivate heritage wheat varieties under exemptions, but quantities are limited and expensive. Medieval roofing did not fail. We deliberately destroyed the supply chain that made it possible. That is not progress. That is engineered obsolescence written into law, and it reveals something important about how technological systems die. Section 8. The economics of medieval thatching. Medieval thatching was not just craft, it was an economic system, and understanding that system reveals why it worked so well. Thatching was local, completely local. The wheat came from fields within 5 miles of the building, 8 kilometres. The hazel for spars came from coppiced woodlands managed specifically for that purpose. Coppicing is cutting trees to the ground every 7 to 10 years. New shoots grow from the stump. These shoots are harvested for poles, spars, liggers. A well-managed coppice woodland produced spars indefinitely. The same trees, cut in cycles, for centuries. The turf or birch bark came from common lands where peasants had harvesting rights. Nothing was purchased from distant sources. Nothing required long-distance transport. This created economic resilience. A village with 1,000 people needed perhaps 5 thatchers working full-time. They trained apprentices. Knowledge transferred directly. In Norfolk, thatching was so important that special measures were used. The standard bundle of water reed was defined precisely, 24 inches in circumference, measured 12 inches from the butt, 60 centimetres, measured 30 centimetres from base. 6 bundles tied together, measured 6 feet around, 1 fathom. Orders were placed in fathoms. 100 fathoms equaled 600 bundles. This standardization allowed trade between regions. Quality could be assessed. Prices could be compared. But here is what made the system sustainable. Thatching was expensive in labour but cheap in materials. A peasant family might spend 3 months of labour to thatch their roof, but the materials cost almost nothing. They were harvested from common lands or waste areas. In a subsistence economy where cash was scarce, this worked perfectly. Compare this to modern roofing. Asphalt shingles are cheap in labour. A crew of 4 can roof a house in 2 days. But materials are expensive. Petroleum products ship globally. The economic calculation is inverted. Medieval thatching made sense when labour was abundant and materials had to be local. Modern roofing makes sense when labour is expensive and materials are globally traded commodities. Neither is inherently better. They are optimised for different economic conditions. But what we lost is resilience. Medieval villages could maintain their roofs indefinitely with local resources. No external supply chains required. Modern buildings are entirely dependent on global industrial systems. Supply chain disruptions mean no roofing materials. During COVID-19, asphalt shingle shortages delayed roofing projects by months. Prices doubled. A medieval village would have been unaffected. They would harvest reed, cut hazel, thatch roofs. This is the hidden cost of efficiency, vulnerability to systemic disruption. Section 9. The physics of why it worked. So why did this system work so brilliantly? The answer lies in principles of physics. The medieval peasant understood intuitively. First, water shedding. Medieval thatched roofs were built with a steep pitch, 45 to 55 degrees. This steep angle is vital. On a gentle slope, water moves slowly, velocity is low, time to penetrate is high. On a steep slope, water moves fast, velocity is high, it runs off in seconds. The steep pitch ensured rainwater gained velocity and was shed before penetration. The smooth compacted surface enhanced this. No rough spots to catch water, no depressions to pull water. Modern shingle roofs use a similar principle but rely on overlapping barriers rather than shedding speed. Second, the composite multi-layered defence. Thick thatch as primary shield, turf or bark as secondary shield, breathing system to prevent condensation. Each layer had a specific function. Together they created redundancy. If rain penetrated the outer 6 inches of thatch, it hit compacted layers below. If it penetrated those, it hit the turf underlayer. If it somehow penetrated that, the roof structure below was often treated with smoke or tar. Defence in depth, no single point of failure. Third, thermal performance. The combined thickness of thatch and turf created massive insulation. Air pockets trapped within straw are one of the most effective natural insulators known. Modern fiberglass insulation works on the same principle, trapped air. But thatch has advantages fiberglass lacks. Thatch regulates humidity. It absorbs excess moisture and releases it slowly. Fiberglass loses insulation value when wet. Thatch maintains function even damp. Studies have measured thatched roofs at R48. 30 centimetres provides R48. Modern building codes require R30 to R40 for cold climates. Medieval buildings exceeded modern standards, passively, with no manufactured materials. Fourth, resilience and repairability. The cruck frame could flex under loads that would collapse modern trusses. Oak beams can bend 30 degrees and return to shape. Modern engineered lumber snaps at 10 degrees. The stitch thatch could withstand winds that would strip shingles. Wind tunnel testing shows that roofs remain intact at wind speeds up to 90 miles per hour, 145 kilometers per hour. Modern shingles fail at 70 miles per hour, 112 kilometers per hour, and damage was easily repaired with local materials. A section damaged by falling branch could be patched in hours with straw and hazel. Modern roofing requires specialized materials and professional installers. Medieval roofing could be maintained by anyone with basic training. This combination, water shedding, multi-layer defense, thermal performance and resilience, created a system engineered for the long haul. Section 10. The modern archaeological window. Here is something remarkable. Medieval thatch is providing modern science with an archaeological window into the past that exists nowhere else. Remember the smoke-blackened thatch we discussed earlier? Approximately 250 buildings in southern England still have base coats of thatch applied over 500 years ago. These layers, protected beneath fresh coats added over centuries, contain perfectly preserved plant material from the 1300s and 1400s. Archaeobotanists can examine seeds and crop weeds mixed in with the straw and identify plant species. Many are now extinct. One analysis identified 16 plant species no longer found in that region. Climate change or agricultural practices drove them to local extinction. But their seeds remain, preserved in thatch. This has allowed scientists to reconstruct what medieval fields actually looked like, what weeds competed with crops, what the ecosystem was. They can also identify wheat varieties. Medieval wheat had characteristics modern wheat lacks: longer stems, different seed heads, different grain properties. Analysis of the grain still attached to some thatch straws has revealed genetic information. Scientists are now attempting to recreate medieval wheat varieties from this genetic data. Why? Because those varieties had traits valuable for modern sustainable agriculture. They grew tall in poor soil without fertilizer. They resisted lodging, falling over in wind. They produced straw valuable for multiple purposes. Modern short-stemmed varieties require high fertilizer inputs. They are optimized purely for grain yield. Medieval varieties were optimized for total farm system efficiency. The thatch is also revealing diet information. By examining which grain types were used for thatching, researchers can infer what people were eating. Rye thatch suggests rye bread. Wheat thatch suggests wheat bread. Mixed grains suggest maslin bread. In one region, thatch analysis revealed a shift from wheat to rye around 1450. This correlates with known climate cooling that made wheat harder to grow. The thatch recorded the agricultural adaptation in real time. This is not abstract academic research. This is practical information about how agricultural systems adapt to climate change. Information directly relevant to modern challenges. If you love uncovering the forgotten wisdom that made the medieval world endure, subscribe for more stories that bring history's craftsmanship back to life. This channel explores the engineering, the economics and the knowledge systems that let medieval people not just survive, but build things that lasted. Let me know in the comments what piece of lost technology you think we should investigate next. The medieval blacksmith steel that lasted 800 years? The water management systems that irrigated without pumps? The food preservation that worked without refrigeration? Thanks for watching.